So if you have a vector A, whatever A might be, x-axis, y-axis, this is your vector A, I can write A in a convenient way in the following way. A times A hat. Now this notation can make a number on in people's mind when they're not used to vector notation. Because there's 3 A's here written, one equation with 3 A's, they all refer somehow to the vector A, yet each one of these A's means something different. If you don't understand that, you will have trouble with this notation of vectors in electric fields and adding forces and so on. So it's important that you understand what's the big difference between all of these things. Okay? A lot of times people, maybe writing quickly or so on, when they're talking about a vector, they just write the letter. Okay? So A in this equation, it's the standard way to write this, is the magnitude of the vector A. How long is vector A? That's what we call the letter A without putting any hat, without putting any arrow on top. That's usually the notation for the magnitude of the vector. Okay? Magnitude of the vector. That's why we put these 2 bars. How big is the vector? Okay? If that is true for A, if A is as big as the magnitude of the vector A, right? Then notice that this A hat vector that I put here must satisfy this. Well, the magnitude of A is the magnitude of this thing, which is A is just a number, and we have the magnitude of A hat. But A, the magnitude of A and A are the same thing, right? They're 1. This is, you can divide by A, both sides, which tells you that the magnitude of A hat is 1. Any vector that has a magnitude of 1 is called a unitary vector. So by writing a vector A this way, you decompose the 2 important properties of a vector, and you've written them separately. What are the 2 important things of a vector? A vector has a magnitude, which answers the question how long, how strong, right? And a vector has a direction. The magnitude, I have already placed it here. A doesn't have any information about how big the vector is because any unitary vector has magnitude 1. So the information about the magnitude of the vector is not contained in A hat. What A hat contains is the direction of the vector. So you split the vector into information about magnitude, information about direction. In which direction is A hat pointing? A vector divided by a positive number points in the same direction as the vector, but it's just smaller or bigger, right? So A hat must be pointing in that same direction. What are the components of A hat? Find the components of A hat. What's the X component of A hat and what's the Y component of A hat? Say it again. Nope. Think about the magnitude of a vector that has components. So you're saying, actually what you're saying is this, 1, 1, which is the same as writing 1 times I hat plus 1 times J hat. Is the magnitude of this vector 1? It isn't. Square root of 2, right? So in terms of magnitude, that's not satisfying what we know about A hat. And also the direction. A hat, if the components were 1, 1, in which at what angle would it be pointing with respect to the x-axis? 45 degrees, right? But A doesn't have to, A is any vector, right? So let me help you there. A is making an angle theta with the x-axis. So what are the components of A hat? Cosine theta and sine theta. How do we know that? Well, what's A? The whole vector A, magnitude and direction, is A cosine theta, right? In the let's write in the x direction, and a sine theta in the y direction. This is the same notation as a cosine theta in the I hat direction plus a sine theta in the j hat direction. Right? This is exactly the same thing. They just mean the same thing. So what happens when you take a and you divide it by a? The vector a, and you divide it by the magnitude of the vector. You should get what? Vector a divided by the magnitude of a is equal to what? Vector a divided by the magnitude of a is a hat. So what I wrote here, when I divide by a, what's left on the right hand side should be a hat. Therefore, well, this is 1, of course. This is a divided by a is 1. So you end up with cosine theta for the x direction and sine theta for the y direction. A hat has components cosine theta and sine theta, x and y directions respectively. So this little vector a over here, if you were to draw the components, this side of that little vector would have a magnitude cosine theta, and this side of the vector will have a magnitude sine theta, which is the same angle as the big vector a is making with the horizontal, right? A hat and a point in the same direction. So if I have a particle here, say Q1, and I have my test particle over here, the vector that goes from particle 1 to the test particle, that's the vector that I was talking about there. That's 1t. From 1 to the test particle. Draw a vector, a line starts with one, ends in the other, that's your vector. So what is the vector r hat 1t? Actually, I just call it qt, right? Let's just keep the notation same. So that little vector is the same as this vector in terms of direction. It points in that direction also, but instead of having whatever magnitude this one has, 3 meters, 5 meters, a mile, it has a magnitude of 1. Right? 1 meter, or whatever units you're using. So this is r hat 1t. So in this equation we have the vector that is coming from the interaction between 1 and the test particle, right? That vector, the vector, say force, we could break it up into the magnitude of the force, and the direction is going to be in the direction of the vector, unitary vector that goes from 1 to the test particle, right? Depending on the sign of the charges, the force might be along r1t hat, or it could be opposite to r1t hat, right? If the two signs are opposite, if this is positive and this is negative, then r1t hat points in this direction, and the force between them points in the opposite direction, right? Because the two q's, this q and this q, have different signs, therefore that puts a minus sign in front of the vector, right? So that's how we describe the equation. That's how we use or wrote down the force between Q1 and whatever charge Q2, right? We wrote it like this, Q1, Q2. This is the force that 1 puts on 2. I should specify that clearly. 1 on 2, we wrote it this way. R12 squared. This is not the vector, this is the magnitude of the distance between the two charges squared. And we wrote it this way, R hat 1 on 2. So if this is Q1 and this is Q2, the force could be attractive. If the force was attractive, it was because one was positive, the other one was negative, right? So the little vector R1, 2 hat points in that direction, from 1 to 2, magnitude 1. But if the two charges are different signs, one is positive, the other one is negative, the force points in the opposite direction of that vector, right? This vector over here is the force of 1 on 2, and we're assuming that Q1 is positive and Q2 is negative, okay? The same equation tells you that if Q1 was positive and Q2 was positive also, then your little vector r hat 1, 2 hasn't changed. That just depends on, goes from 1 to 2, magnitude 1. But now your force will be pointing in the same direction because the two charges have the same sign. So this will be now your vector force between 1 that 1 puts on 2. Okay? So this is how we put that direction, attraction or repulsion, in when using an equation like this with the vector r hat.